the last couple of video lectures and PowerPoints, we were really focused on this concept of non-steady state versus steady state exercise, or what happens if you immediately start exercising at a state that is, or at a rate that is super high, and you're not able to reach that VO2 steady state, or you have a slow increase of kind of aerobic metabolism, and you're able to hit steady state and maintain that steady state exercise. What we're going to be talking about in this YouTube video is what happens when you stress the system in a different way. What happens when you intentionally stress the body in a different way. And what I mean by that is kind of really putting the body through this incremental exercise test, or this incremental GXT, or graded exercise test. And essentially what you want with a graded exercise test is you want to continually stress the body and make it hit a steady state, and then have somebody chill and hang out at a steady state, and then stress the body, and then chill and hang out at a steady state, and then stress the body, and then chill and hang out, and then right? Like, you kind of get the point. Really what we're looking for with graded exercise tests is a stair step. So we go up, steady state, up, steady state, up, steady state. And the reason we're doing that is because we want to really kind of test to see how hard an individual can work. How high can we tax, or how much can we tax their aerobic system? How much can we push the individual? Incremental exercise tests, or GXTs, are usually set up so they have like these 1 to 3 minute work stages. After 1 to 3 minutes, you end up either increasing the speed if you're on a treadmill, or you end up increasing the incline on the treadmill. If you're on a bike test, or you're doing a bike test, you end up adding a mechanical resistance, or adding an electronic brake to the flywheel. You can kind of think about this as kind of putting someone on a hill on a bike, or you can kind of think that you're making it harder for them to push the pedals. You're making it a harder exercise, so you're taxing the individual a little bit more and a little bit more and a little bit more as you apply the brakes. So the theory is that we want to get an individual up to their maximal oxygen uptake. So we talked in the last video, about this concept of Vo2, and that's the volume of oxygen that is able to be consumed and utilized. Well, when we put that little subscript max at the bottom of it, all we're doing is we're saying that it is the maximal amount of oxygen that an individual can consume and utilize. It is largely considered the best test for cardiovascular fitness, and it is the gold standard for cardiovascular fitness. And what it looks like is it tends to be a graded exercise test. When you start getting into some of the nuances of the Vo2 Max, well, what it is it is a plateau of oxygen consumption that we can actually measure, and we'll talk about that, but you can actually collect the gases and control the amount of gases that are going into the human, and you can see how much oxygen they're consuming and how much CO2 they're producing. We'll talk about that again. But what we're looking for is this very specific plateauing of oxygen consumption. We're looking for this very specific plateau, right? And what that plateau means is that as we increase work rate, their oxygen consumption does not change. So their body is working at such a level that we cannot adjust and try to increase our energy production, because the body can't do it. Essentially, you have pushed the body to its highest level of aerobic metabolism, or the highest level of its ability to produce and maintain, or kind of just not maintain, but produce a work rate. It's not often that you actually see this physiological plateauing that occurs. And truthfully, I've only seen it a couple of times in Vo2 Max testings. And that's for several reasons. Some people think that it's that you're not really working with individuals that are willing to push themselves to such an uncomfortable place. And if you've never done a Vo2 Max test, you need to, because they suck. They are brutal. You're running around with a mask on your face on a treadmill at an incline. It's awful. But it takes a special sort of person to kind of find that pain cave and continue through it, right? It's if you have an individual that does not hit that very clean plateau, or you increase the work rate and their VO2 does not change, and they sustain that work rate and their VO2 still has not changed, then it's going to be called a VO2 peak. And what a VO2 peak is it's their maximal volume of oxygen consumption that you saw that they were able to attain but not maintain, essentially. And you can there's different ways that you can operationally define a VO2 max. You'll often see that it's there's a heart rate cutoff, and there's a respiratory cutoff, and there's a exertion cutoff. So you can call a VO2 peak a VO2 max. It's just something to think about as you're getting into exercise testing and prescription. But a VO2 max is the maximal volume of oxygen that an individual can consume and utilize. The higher the VO2 max, the theoretically more cardiovascularly fit the individual is. And I want you to know that it is not always possible to see this infamous plateau. Very often you'll see someone kind of peak and then drop again because they can't maintain the work rate, or they can't maintain that that exercise level. Another concept that you really start to see with these graded exercise tests, or it doesn't even have to be a graded exercise test, it can be a different type of exercise test, is a lactate threshold. So if you guys remember, in glycolysis, we talked about pyruvate going towards acetyl-CoA. Well, there's actually a different fate of that pyruvate that we will talk about. But essentially, a lactate threshold is it's kind of this inflection point that occurs in the accumulation of a molecule called lactate. And if you look, you can kind of see that, for some reason my finger's not working on the trackpad, you can kind of see that right around this area, somewhere between 250 and 275 watts, which is work rates down here on the x-axis, you can kind of see that the blood lactate concentration of this untrained individual kind of hits a point and then boom, right? It's a nonlinear increase. It's actually an exponential increase. And so that point at which you kind of start to see, I mean, you could probably call it 275 watts, becomes this nonlinear increase, right? It's no longer this straight line going. It's actually, there's this overwhelming accumulation of lactate that's occurring. With training status, you can actually push that curve to the right, and you can see that this kind of nonlinear increase, this exponential increase, is really occurring somewhere around this 325 watts. So the trained individual has a lactate threshold that's significantly higher. And that's what we're going to be talking about over here on the left-hand side, right? Untrained individuals have a lactate threshold of about 50 to 60% VO2 max. And trained individuals have a lactate threshold of about 65 to 80% VO2 max. There's also this concept of the onset of blood lactate accumulation. And what OBLA is, or what onset of blood lactate accumulation is, it is a very specific point of lactate concentration that it denotes, right? And most times you're going to see it as 4 millimolar. So if we go over here, OBLA, or 4 millimolar, is occurring at 300 watts, or just before 300 watts for the untrained individual, and about at 350 watts for the trained individual. So OBLA is going to be the point at which the body, when you measure the blood, there's 4 millimolar concentration of lactate inside of the blood. Lactate threshold is the inflection point, or the time span, or the point at which you go from linear accumulation of lactate to nonlinear exponential accumulation of lactate. Okay, Dr. Hyde, you're sitting here, you're talking at me, you're saying all these words, you're saying lactate a lot. I don't even know what it is. We haven't talked about it yet. Well, I did this on purpose because you now know the entire pathway of glycolysis, and you know the fate of pyruvate really, really well, or so you thought. There's actually two different fates for pyruvate. One fate, which is what we typically see with something like steady state exercise, is going to be the taking of pyruvate, the two pyruvate molecules that are generated from glycolysis, and moving them over into the Krebs cycle or the TCA cycle, right? We're going to convert the 3-carbon pyruvate into a 2-carbon acetyl-CoA, and we're going to pump it through Krebs cycle. Well, there's also another fate that I want you guys to know. And that other fate of pyruvate is the lactate pathway. And what's going on with lactate is that it is a product that is made immediately after pyruvate. And it's actually kind of what most people use to denote the difference between anaerobic and aerobic glycolysis. So if you're producing a lot of lactate, it's going to largely be considered an anaerobic production path because we're not using oxygen for it, right? And we don't even have to have oxygen to produce it. So lactate is the other production product from pyruvate. Kind of interesting, right? That makes these two slides make a lot more sense, because if we're continually working at a lot higher work rate, we're going to eventually hit a non-sustainable sounded like Bugs Bunny there. We're going to hit a non-sustainable work rate. And when you hit that non-sustainable work rate, what happens? Well, we're going to increase the demands on the anaerobic systems, right? We're going to start increasing the phosphagen system and start increasing the glycolytic system, because we're going to need that energy faster than we can produce it with the aerobic, which is why we talked about this stuff last lecture. So if lactate's being produced when we're at high work rates, what's going to be controlling it? So if you're saying that lactate is an anaerobic point, loosely, if you're saying that lactate represents an anaerobic generation or an anaerobic glycolysis, then would this lactate threshold also be considered an anaerobic threshold? It would make sense to reason that, right? And truthfully, historically, it's been called lactate threshold is correlated with your anaerobic threshold. It's not technically the most scientific approach to it. It's not technically the most accurate approach, because it's not that the muscle is anaerobic. It's not that the muscle is lacking oxygen in the environment. It's that there's other factors present that are controlling the rate at which ATP is being produced and the rate at which lactate is being produced, if that makes sense. So while lactate production is a kind of like a proxy of anaerobic glycolysis, it doesn't mean that there's not oxygen that's occurring when you're seeing things like OBLA or lactate threshold. So kind of interesting is that the conversion rate of pyruvate to lactate is not necessarily going to be exclusively driven by the presence of oxygen, especially whenever we're going to be working out, especially whenever we're going to be exercising, because our body's going to be taking in big breaths and breathing. So we're going to be pulling in oxygen. So it's not that we're in an anaerobic state, but we're actually going to be somewhat manipulating the directionality of pyruvate and really the fate of pyruvate towards either lactate or towards Krebs cycle, towards acetyl-CoA via the NAD/NADH ratio. And while this might get a little bit deep, I think it's really an important way to understand metabolically what's going on with lactate and why it's been so maligned for so many years, but also kind of give you a little bit more insight into what's going on physiologically in the body as we're trying to figure out what's happening with exercise and when we're trying to work with individuals, right? So Krebs cycle, as you guys remember, and you should remember this table because it was in our last module, Krebs cycle is going to be stimulated and inhibited by the NAD and NADH ratio. And what that means is that in a low or in a high NAD and in a low NADH environment, the Krebs cycle is going to try to spin up some more, because remember, we want to make sure that we have this kind of Goldilocks place of energy. And if we have a high NAD amount, if we have this high NAD concentration, that means we have we're not capable of producing ATP as fast, or we're not readily producing ATP. So we're going to try to speed up the Krebs cycle. If we start to experience buildups of NADH, whether this is because electron transport chains actually getting backed up because we have so much energy, or there's several other reasons, but if we start having this buildup of NADH, we're actually going to start slowing down the Krebs cycle, because we can't turn that thing any faster than it is already going when it's maxed out. So what happens when we have this increasing amount of NADH? And that's actually going to be that we start kind of slowing down the conversion of pyruvate into acetyl-CoA, and we start ticking this sucker up, right? Like, we start generating more and more lactate because we're donating hydrogens here. We're moving a pyruvate towards lactate via NADH. So instead of using the NADH to just power the electron transport chain loosely, we'll say, we're actually using it to fuel the conversion towards lactate. So it's not, if we're using such an important molecule like NADH, it's super important, then that means that we have a very specific need for that lactate, right? Like, one, we're trying to get through this ATP generation fast because we need the ATP. But would our body really waste such an important molecule like NADH to produce lactate if it was a trash product? And I don't really think that it would. So that's kind of a big deal. Like, that's kind of important, right? Like, it means that our body has a higher thought for that lactate. This is essentially, the slide's just putting into words what I was saying earlier. But there's also, if you take and you go a little bit further onto this lactate concept, it's not just the NADH that's going to be driving this conversion to lactate. Stress hormones are also going to be driving the conversion to lactate. So stress hormones, specifically epinephrine and norepinephrine, are going to minimize the amount of NADH that can get into the mitochondria. And that's important because that's where the electron transport chain is. So we're actually going to have stress hormones that start moving our body towards faster ATP production. Think getting away from the tiger or fighting the tiger. You got to make energy, and you got to make energy fast, and you need that energy right now. If you're trying to overhand right or hit a 1-2 on a tiger, you got to be able to generate that energy fast. And so our body's actually trying to tell us, hey, don't go this way, go this way, make the lactate and produce the ATP fast. Something else that's really important to know is that different fiber types, and we'll get into this more, but different fiber types such as fast twitch or slow twitch, or anaerobic and aerobic, or fast and slow, muscle fibers have different concentrations and different affinity level lactate dehydrogenase enzymes. And this is getting really into the weeds, but it actually explains why endurance athletes get lower lactate values than sprint athletes. It explains why bodybuilders are able to get higher lactate values than individuals that lift weights for hundreds and hundreds of reps. So you can actually kind of condition your body to handle lactate or to clear lactate. So the faster twitch fibers actually create lactate a lot faster. And that's what you're seeing in this graph. I don't want you guys necessarily to know that for a test, but it's just kind of an interesting piece of information that I hope kind of starts to tie some of this information together for you and why it's so interesting. And I think that this is funny because it's kind of like Spider-Man, pointing to the different Spider-Mans. And I hate people that explain memes, but you can kind of think that it's the three different ways that we're controlling lactate, right? Like, it's NAD, it's hormones, and it could be the muscle fiber type. And I butchered it because I explained it. Super important is lactate is clearly not going to be a dead end molecule. We're putting so much energy into making lactate that there's no way our body's going to just piss away that. And well, technically you're not going to urinate it out, but essentially lactate's not going to be this devil that a lot of people try to make it out to be. And in fact, if you follow this diagram, you can see that we take glucose, we turn it into pyruvate. Pyruvate gets converted into lactate. Lactate will then actually get shuttled out of the muscle cell and into the body, into the bloodstream, will actually flow to our liver. And when it hits our liver, we can actually convert it back into glucose and then shuttle that glucose right back in. So what we're doing is we're literally taking and burning a fuel, taking a product, and then recycling and burning that fuel again, right? Like, how cool is that? We're literally just recycling carbons here, and we're just recycling carbon skeletons so that we can continue to burn it. So we're burning glucose, and then we're making glucose, and we're burning glucose, and then we're making glucose. It's kind of a cool self-fueling, self-generating cycle, right? A couple important things I want you guys to know, that this you do need to know. Lactate's not a dead-end molecule. I've beat that to death. It doesn't cause soreness. Lactate is not the reason that you get sore after workouts. That's muscular damage. It's actually that you have injured your muscle. That's what's causing soreness. And it's not the cause of muscle burning, right? That's hydrogen ions. That's acid. Lactate is not necessarily lactic acid. The book does a great job explaining these differences. Right. On to the next one.